Okay, so we've been working with the substitution method for finding antiderivatives, indefinite integrals. And now we want to try and take that strategy and use it to evaluate some definite integrals. So the main thing to remember is that you can do it. And yes, that's a little pun. When you're done laughing, we'll move on to the next slide. So here you can see we have a definite integral, and there's a composition involved, so our strategy will be to go ahead and do u-substitution, and you start the exact same way you did for indefinite integrals. We're going to start by choosing a u, and remember we usually choose the expression that got plugged into the other function. So in this case, we look in the parentheses and we see that we're going to try and choose u as x squared minus 1, just like we always did with our indefinite integrals. And we take the derivative, du over dx, and what is that, 2x? And then we solve for dx, and that is du over 2x. Nothing's changed there. But before we build that new integral, this is where a new step comes in. Because when we're doing definite integrals and using u-substitution, one of the methods that works most efficiently is to stay with u because u is good. And by that what I mean is I'm going to convert these x numbers. -2 and 1 are x values. And we want to convert those to u values. So we plug each of those into the expression for u, and we get a new value. So that b value that's a 1, when I plug b into u, I get 1 squared minus 1, which is 0. And when I take that -2, the a value, and I plug it in, I get 4 minus 1, which is 3. So these are going to be our new limits of integration. The 3 will go where the -2 is, and the 0 will go where the 1 is. Don't freak out because the 0 is less than the 3. We're putting them in the positions that they're associated with. So here's that new integral. We're built just like we did with our other substitution method. We build that new integral. So we're going to have 2x times u squared, because we're substituting u for x squared minus 1. And then instead of dx, we'll write du over 2x. And just like before, some stuff is going to simplify and cancel. Luckily, these 2x's are gone. And then instead of putting the -2 and the 1, we'll put the 3 and the 0. So we have this, when we clean this up, we have this integral from 3 to 0 of u squared du. And the antiderivative for u squared is u cubed over 3. And our limits of integration this time are 0 and 3. When we plug in 3, when we plug in 0, we get 0 cubed over 3, which is 0. And then when we plug in 3, we get 27 over 3. 27 over 3, which is 9. So this whole thing works out to be -9. Remember, with definite integrals, you do not come up with an expression for an answer. You come up with a value, a number, right? This represents that value for the definite integral, the area under the curve sort of thing. So there's no reason to convert this integral back to x values because we changed the limits of integration right here and plug those values in here. We can stay with u because u is good and just stick with those u numbers and compute the value. It saves us a little bit of work to do this math up front. Yes, you could take it back to x and use -2 and 1 again, but you end up doing the same calculation. So I am recommending that you stay with u because u is good. Convert your limits of integration when you choose a u, and then set that new integral up using those values. Let's try one more example. Here again we have a composition for our expression and we have a definite integral. I'm going to try and talk a little bit less this time and run through our process. As usual, we choose u. I'm going to do 4x squared plus 1 for this one. So u equals 4x squared plus 1. The derivative is 8x. And that means that dx is du over 8. 8x, excuse me. And then, like I mentioned, the new step for these definite integrals is that we are going to convert the limits of integration. We're going to stay with u because u is good. When I plug 0 in here, I get 0 plus 1, which is 1. When I plug -1 in, oops, I've been using the colors here. Let's see if I can fix that. Yep, I can. Plug it in -1, and that's going to be 4 plus 1, which is 5. So I've converted my limits of integration, and now I'm ready to set up that new integral. I'm going to write this over here on the right this time. I usually make the new integral in blue. So the new integral is not writing. What happened? Oh, there it is. Sorry about this. I'm too lazy to go back and do a second take. So let's just keep it rolling here. There it is. The new integral. We're going to have -16x over u squared, because we substituted in u for 4x squared plus 1. And then we're going to substitute for dx, which was du over 8x. Again, we have some canceling going on. The 8x and the -16x make -2. And when I rewrite this, and I forgot to put in my limits of integration. I got a 5 down here and a 1 down here. Don't freak out that the numbers aren't in order. The minus in the fundamental theorem will take care of all that. Okay, let's rewrite this thing. I'm going to factor out the -2. I'll go from 5 to 1, and then this is a u to the -2 du. And the antiderivative of u to the -2 is -u to the -1. That multiplied by -2. So this is 2 over u when you do the antiderivative. Let me just write it over here. It's -2 times -1 over u, and that equals 2 over u. Limits of integration are 1 and 5. So what are we going to end up with here? 2 minus 2/5. And what is that? 10/5 minus 2/5. That's 8/5. 8 over 5. So the value of this definite integral is 8 over 5. And again, in this step, we kept those u values. We changed the x values into u values, and we stayed with u because u is good. Okay, so there's not a lot of new things going on here. The main thing is remember to convert the numbers. When students first start working with these definite integrals and u-substitution, they forget to change the limits of integration. So some people would do this problem, they'd stay with u, but they'd use -1 and 0, and they'd get the wrong answer. Okay, so we're going to practice this and see how it goes. And then if we ever end up having an actual day of school, again, we'll meet in person and I can answer questions. Okay, so one more time, just to drive the point home. Remember, stay with u because u is good.